Good morning, here we are. Once again, it is the Physics 2A video lecture. Physics 2A video lecture 11. And the last one got cut off a couple minutes before the end, so I'm gonna fill in what you guys missed there. It was only about 2-3 minutes. But that's why we'll go back to the catenary for a moment here. The catenary, that's the shape that the hanging chain takes, and very beautiful. And I had told you last time it's the hyperbolic cosine, if you wanted to look that up, the mathematical function. And the application we had looked at was the suspension bridge. There's one more important application, and that goes as follows. So we have this curve here. I'm not even going to draw it. I think you can see the chain. And the principle now is that the tensions are tangent everywhere. So at the very top, the tension would be in that direction, right? The tension's a force, and the force is distributed throughout the chain, tangent to the curve of the chain. So suppose you were to take a rigid chain. Oh, one more thing. And the general force of gravity, the weight, is just pointing down. Okay, the weight is pointing down. So now what we're going to imagine is we take this chain, this structure, and we make it rigid. Okay. So make this shape, a material in this shape, make it rigid, and then invert it and stand it up like this. Well, there's a very famous structure where they've done just that. It's called the Gateway Arch in St. Louis. So that's what you want to add to your list of pictures. So this is called the Gateway Arch. It's not the only place this principle has been used, but the principle is this. The forces are acting down, the weight is acting down, but because of the shape here, those forces are being transmitted exactly along the curve, all the way down to the ground here. So the tendency to buckle is eliminated from this arch. So you could say this is the perfect arch in terms of eliminating buckling. And what I had written down in the last 3 minutes that were cut off of video lecture number 10 was that I wanted you guys to get images of all of these things, starting with the post and lintel, the Roman arch, the Gothic arch, the Pantheon, etc. I want you to have images of all those things, print them out, and insert them into your lecture notes. Okay, so you can find really nice pictures of all these things and print them out. So this was the homework. Now, you may have already done some of this, but if not, print out images. You can get a screen capture for, and I'll put that little list right here. So we had post and lintel, we had Roman arch, and you're going to find beautiful things if you look these up. We had Gothic arches along with flying buttresses, and then we had the Pantheon in Rome, and then we had suspension bridge and Gateway Arch right there. Gateway Arch. Okay. So if you get printouts of all those and look them up, it'll be interesting to you. Okay, that was from last time, that was left over. Now we're going to go back to the force and vector concept. we had forces add like arrows. So that was our vector concept. And the demonstration that I want to analyze once more was when we had these two scales here. Okay. And we had a weight, which was just 10 newtons. Okay. And yet our tensions were more like 20 newtons. Okay. So we want to do this exactly this time. This sketch is adequate for the task. We have, I'll draw in red, these are the two vectors representing the tensions, which are the forces in the string there that are being measured here and here by the scales. And we saw that we had an outward component and a vertical component, outward and vertical. And these get arrowheads on them too. So these two blue vectors add up to that red one. Now the principle is that the net force, which is the sum of all the forces, and we're going to say acting right at that blue dot there, the sum of all those forces, that's Greek letter sigma, is equal to 0. That's when things are at rest. The net force is equal to 0 here. What we're going to do is introduce x and y coordinate system. Gravity is down, so here we have, I'm just going to call this F sub W is the weight. Okay. So that's my weight. We're not going to call it 10 newtons, we're just going to call it F sub W. So now what we have here is in components, we have the sum of the x forces equals 0, and the sum of the y components is equal to 0 as well. And we're going to fill in what we have here. We have an angle theta. I'm going to call this T equals tension. Okay, and we have the same thing on the left side, it's symmetric. So here's how to work this problem, and then I'll assign a couple more out of the text to get practice in this. Okay, here we go. So the x force, the force in x direction, we have, so x, we have this one down there, that's tension T times the cosine of theta, okay? But we also have this one pointing to the left. Okay? That's also minus tension T cosine of theta. And that equals 0. So this one is trivial in this case, okay? Because of the symmetry, these x components, I said last time, is an equal tug of war. They cancel out. However, I'm going to assign a problem where we have one theta here and a different theta there. Now, if you had different angles and different tensions, then this would be the one going to the right, this would be the one going to the left. Okay, so the homework problem is going to be a little more involved. This one is dealt with. Now, in the y direction, we have a t sine theta, and we have another one on the left that's exactly the same. So for that reason, I have 2 times tension sine theta pointing up, those two blue ones, and pointing down I have F sub W, so minus the weight, F sub W is equal to 0. Okay, and in this problem we're going to solve for the tension. So solve for tension T, and what we find is, I'll put it over here, we'll showcase it. What we find is, just bring the force over to the right and divide by 2 sine theta, we find T is equal to the weight divided by 2 times the sine of theta. Okay. And this is the reason those forces can be so large. The smaller that angle theta, the smaller the denominator, the larger this number is itself. As theta goes to 0, if you pull harder and harder and make that flatter, the tension would diverge, would go to infinity. Okay, so the tensions can be very large in a scenario like this. Okay, so this is the skill that we're going to learn and practice. It's referred to as drawing a free body diagram and then evaluating the force equation. Okay, so this is just this is a start, and I'm going to assign 2 or 3 of these for the homework, and you'll practice them, and I'll demonstrate them later on. Okay, so this is for starters. What we're going to do next is forces and Newton's laws of motion. Okay. This is, you could say, this is practice for what follows. Yeah. So now we're getting into the actual meat of the subject here in chapter 4, the laws of motion. So we can title this Forces and Motion. So Newton's laws. When you're talking about forces in motion, I'm just going to discuss what I demonstrated before. This object has a weight, so it certainly has a force on it. It's not moving right now, so it has the weight pointing down. There's also a force that the table exerts on this mass, this object here, that is pushing up on it. Okay. Or if I hold it in my hand, that's better. So the scale told us 10 newtons, okay? Told us 10 newtons, but now let's look at the forces involved. I'm holding it up with 10 newtons, so there must be 10 newtons in the down direction. What happens if I release this thing from rest, right? It'll fall, okay? So that's the, and I also, if I were to slide this across the table, I push on it and I bring it into motion, and there's a force that I'm exerting in order to accomplish that. So we want to talk about forces in motion. The first thing, though, is that there is what's called inertia. If you push on something, it resists being pushed on, and you have to give it some, exertion, exert some force with your muscles. So what you're feeling, that resistance, is the inertia. Resistance to a change of the state of motion. That accords with the day-to-day version of the inertia. You just want to sit there, right? You're resistant to change. So all objects have that as well. And You know, I'm going to bring out the air track again. It's a good idea. Okay. We're back with the air track. So with any luck, I'm going to wheel this over here. Perfect. So we've got a view of our air track. I'm going to turn it on. And I described its functioning last time. So we just have these gliders on a cushion of air. And we can now ask, what's the net force on these gliders? What force is acting on them? And you would answer, well, they have a weight. If I put them on a scale, they weigh a little bit, and the air is holding them up. And those two forces essentially add up to zero. So we can say the net force is zero. I'm going to give this thing a push. As soon as my finger leaves it, it's just gliding, okay? On the way back, it's gliding with constant velocity. The net force on it is zero. On the other hand, if I give it a push, I'm giving it a force and accelerating it, okay? But as soon as it's moving freely here, it has zero net force on it. And if we had patience and a long track, this would just go on forever, never stopping. And so this is actually a demonstration of what's called Newton's first law of motion. That if the net force on an object is zero, it will just continue in its state of motion. It'll continue in its state of uniform motion, which means it'll just go in a straight line. Go in a straight line forever. So you can imagine us if we were out in outer space, no gravity, no nothing, and we give something a little nudge, it would just drift on and on indefinitely. So that's the content of Newton's first law of motion. So let's come on back to here. There we go. Got our usual view again. So yeah, there's the inertia, resistance to a change of the state of motion. And there's different ways to formulate this. Let's put it this way. A force-free object persists in its state of uniform motion. How about that? A force-free object persists in its state of uniform motion. Now this inertia has a measure, and that measure is the mass. Is a measure of inertia. Or is the measure of inertia. There we go. So this is all made concrete when we formulate Newton's second law, namely how the mass and the force and the motion are linked. And that is the following. I'm just going to write it as a formula. The net force on an object is equal to its mass times its acceleration. Or we can write the acceleration of an object is equal to the net force divided by the mass. Now, what this is saying is that the object accelerates in the direction of the force. Okay? But the magnitude of the acceleration depends upon how large that mass is. The larger the mass, the smaller the acceleration, and vice versa. So we can write these in either form, this law in either form, same content. And only now is the concept of mass really even defined. Before we were always talking about weight, we were talking about forces and weights, but we didn't know what the mass is. And the relationship between mass and weight is the thing I like to bring out immediately when I introduce Newton's second law. Before we do a lot of other applications with this, a lot of technical applications, we want to find out about the weight. So what is weight? The thing is, we had the weight as a force, but now we have this other expression for force. So here's my demonstration that I'm only going to draw. It's a thought experiment. So what we imagine is that we have the scale here, and we're hanging our weight from here, a good old 10 Newton weight, and say it's hanging from a string. Okay. Now at this stage of the game, we say there is F sub W, the weight. We'll go ahead and say there's a tension in the string. And in my example, I have a 10 Newton tension pulling up and a 10 Newton weight pulling down. Okay. So this is the first part of our discussion. The second part is if we cut the string. Okay, so there's a string here. We cut that string, and now what happens? Our weight here is falling. Cut the string. Then we have free fall. Well, we know all about free fall. We have free fall on the one hand, and we have F sub W on the other, right? We cut the string, there's no tension anymore. And what Newton's law says is that because we have the law of free fall, acceleration equals F sub W over M. That's this form of Newton's law here. And what is the acceleration? G equals F sub W divided by M. Now all I have to do is multiply across, and I find out that the weight is equal to the mass times the acceleration due to gravity. I'm going to send that up there. And this is a really important result. Let's go ahead and erase this. So continuing this thought here, right? What is weight? There's a demonstration. We cut the string. We go up to there, acceleration G. So we find F sub W equals mg. That's to say the weight is equal to the mass times the acceleration due to gravity. From now on, we're always just going to write m times g whenever we have a weight. So immediately write down m times g. mass times the acceleration due to gravity. Before I get to the dimensional discussion, oh yeah, so here's the important thing about so we're going to say mass versus weight, okay? Or instead of versus, let's just say not equal to weight. Mass is not equal to weight. What mass is the amount of matter and what the weight is the force due to gravity. Force, or right, gravitational force, okay? Gravitational force. Okay. And to show you the difference, I'll just bring out my scale, this chunk of metal, 10 newtons as usual, close to, okay? So, what if we took this scale to the moon? Up on the moon, this chunk of metal would be exactly the same as it is down here on Earth, but the gravitational acceleration on the moon is 1/6 the gravitational acceleration on Earth. So this would only be about 1.5 newtons on the moon. Take this scale and this weight up there, 1.5. The amount of matter in here is still the same. If you ding your head with it, it's going to feel the same, okay? So that's the mass. The weight is dependent upon the local gravitational force. So that's an important difference. And once we have that, we can really make a lot of progress. So far I've only talked about the inertia, and we now have to talk about the dimensions of these things as well. So let's, we'll start a new board. Systematically now. Fill in all the missing details. So we already knew that the force is measured in newtons. So force F measured in newtons. Now we have Newton's second law. Force is equal to mass times acceleration. Okay. So we know that there's newtons, and we know meters per second squared for the acceleration. The mass itself M has the units of the kilogram. Okay, so that's kilogram. Means 1,000 grams, but that's what we're taking as the fundamental unit of mass, is the kilogram. These masses here are actually a kilogram, okay? Turns out, kilogram, and acceleration in meters per second squared, the Newton, so 1, 2, 3. N has now the units, kilograms meters per second squared. That's the unit, that's what the Newton is equivalent to. And this kilogram, as apparent out of this definition, measures the inertia. If you really want to feel inertia in the absence of friction, what you can do is go to a boat that's at dock, a medium-sized boat, and you can actually push it around in the water, even if it has a mass of many, many thousands of kilograms, because there's no friction in the water. You just give it a push, and you'll feel that resistance a lighter object you can just have move away from you rapidly, that boat is going to move very slowly. So once again, if you want to feel this in your muscles, the acceleration is the force divided by the mass. You can think of the force that you can exert with your muscles, this large mass of a boat, very small acceleration, okay? Good, that's what we want right there for Newton's second law. So this is important to always work out what the units are, and now we see the Newton is a kilogram meter per second squared. Newton's third law and then we'll have all of them. The first law seems to be contained in the second law as well, okay, like a special case. Because when the net force is zero, the acceleration is zero, but zero acceleration means constant velocity. So actually, yeah, let me put that as a note here on the second law before I move on. Note, again, force equals mass times acceleration when F net, and yeah, we're actually supposed to say the net force, that's understood. When net force equals zero, then acceleration is zero, clearly. But acceleration equals delta V over delta T. So when acceleration is zero, velocity is constant. So A equals zero implies V equals constant. And that takes us back to Newton's first law. Okay, one more discussion of Newton's laws. I've talked about Newton's third law now, and then we're ready to do some applications. Third law of motion. This is best done with a picture first. Suppose we have two objects interacting. For example, I'm about to collide two tennis balls with each other. Okay. Then they're going to exert a force on each other. So this is object one and this is object two. And what we say is that, or what we find is that the force that one exerts on two is equal to, in magnitude and opposite in direction, of the force that two exerts on one. Okay, I can actually demonstrate that. With the scales. Okay. Because here I have these two scales. If I hook them together, there we go. Here we go. Okay, see, one scale pulls on the other with the same force. Okay. So these are in contact and they're exerting equal and opposite force. And it doesn't matter if they're moving or not, okay? So they're moving, they still have the equal and opposite force, okay? If they're accelerating, doesn't matter. Equal and opposite force doesn't change. I could do the same thing with scales and pressure forces, and then we would find that they have the same reading when you press them together. So that's Newton's law. It gets a little more interesting when you're not thinking about scales, but thinking about motion. So in the classroom, there's always somebody or half a dozen skateboards stacked up on one side of the classroom. And then we could have some skateboarders stand on their skateboard and push against the wall, and they go rolling out, okay? That's the same effect as if a person were to push you. Okay? So whether you push against the wall and roll out from the wall, or somebody stands there and pushes you, it's the same effect. So you're not used to thinking the wall pushed you, okay? You think somebody pushed you, but it's the exact same effect, and that's because of Newton's third law. So I push on the wall with 10 newtons, the wall pushes back on me with 10 newtons. Okay? And you can demonstrate that with scales as well. So you read about this, it's sometimes said action equals reaction. But the content is that the force that one exerts on two is equal and opposite to the force that two exerts on one. So there's the minus sign, gives the opposite direction. Equal sign says the magnitude, okay. Good, Newton's first, second, and third laws. I'm going to set up a couple of simple problems now with that, starting with the weight concept. So the example with the weight concept is the bucket. So we have a bucket of water. It's got a handle on it, okay, and there's a rope tied to it. And now we say that there's the weight and there's a tension. Those are the two forces on the bucket. But now it's not just going to hold it, we're going to pull it up or lower it down. Okay, we're going to use Newton's third law, Newton's law, Newton's second law. Okay, so there's a bucket with a string. So a bucket with a string. And this is the example of the free body diagram. So I would label this bucket with M for its mass, and then I would write down the two forces acting on it, or any of the forces, all of the forces acting on it. In this case, there's the weight and the tension. Okay, so one free body diagram plus label. So label your free body diagram with the forces. Okay. The implied thing is that we have a coordinate system here. The second step, and always do this, write down Newton's second law. Write down Newton's second law. It's true, right? So you wrote something down that's true. Nothing bad can happen. So you write down Newton's second law, and then you evaluate it. Your third step, the left side, the net force is given by the tension pointing up, and get a minus sign for the weight pointing down, equals mass times acceleration. So now we've filled in for Newton's second law for this bucket problem. And the final step is to solve for whatever you're interested in. In this case, we're interested in finding the tension. Find the tension. So we solve for the tension, get a very interesting result, simple result, m times g plus m times a. I brought the mg to the right side, or you could say tension equals m times g plus a. Okay, that's a simple result, but it's worth analyzing. First of all, if the bucket's not accelerating, then the tension is just the weight. That's what we started with. If we're accelerating in the up direction, the tension is increased. Tension's increased, and instead of a bucket, I can use this weight. I have to do it in slow motion, right? So here's the tension, 10 newtons. If I accelerate upward, you're going to see this pointer go to a higher weight briefly. Okay, that was the effect. I accelerated upward, the pointer went. That was the slow motion. I accelerate up, and the dial is at a higher weight. Okay, so you can see that. And the other effect is if I accelerate downward, you can see the pointer go to a lower weight. Okay, briefly. And finally, so those are all the examples here. Finally, if I cut the string, tension is 0, acceleration equals minus g. Okay. So let's put that as a final note. Cut the string, then T equals 0, because the tension in the cut string is 0. Then acceleration equals minus g. G is a positive number, acceleration is down. That makes complete sense. So yeah, put a couple words in there, a couple more words. So that's a really crucial example. And I think I will assign some problems now, and then we'll have something to discuss next time. Yeah, that's a good start on this chapter. Next time we have a whole number of different forces to discuss. So here's some room. So our homework for lecture 11, chapter 4, problems. Let's see what we had here. Now, I had some last time I didn't get around to writing down. Let's start with those. 35A, 39, and 75. 35A, 39, 75. Those were static problems. Let's get some dynamic problems out here as well. In fact, I think this bucket problem is present in some form or other. And that might be good to work on. Well, it's a two. We're going to save the two-body bucket problem. Yeah, this will be a good one. Number 10. 10 is a dynamical problem. Newton's law. Nothing can go wrong using this one right there. Okay, good. See you guys next time.